Now this is the second question, and as we can see from the marks, it's a long question, so it's a section B question, getting a little bit more complicated and expecting some deeper thinking from you. We're told a camogie goalkeeper on a level pitch hit a ball straight up into the air, and the path that the ball travelled can be modelled by this function here, f of t equal to minus 4t squared, etc. This is a quadratic function, and it's a minus quadratic function, so we know that it is n-shaped, which is exactly what we expect from a ball. So instead of x, we have time on the horizontal axis, and we have height on the vertical axis. So height is my y value, and t, time, is my x value. At what height was the ball when it was hit by the goalkeeper? Okay, so this is a really kind of odd question, odd way of phrasing of it. So the first thing to answer this, we first need to say, when was it hit? When was it hit? Well, it was hit at the start. And at the start, that means time is equal to 0. So if you're not sure with questions like this, the start of these questions, you're usually calculating either having the output equal to 0 or the input equal to 0. So this will be 4t by 0 squared plus 16 by 0 plus 1. And you could have done this without even writing it down. That is 1 meter. So it actually starts here at 1 meter. At 1 meter, like that. Okay, they didn't ask you to draw a graph of this. I just wanted to have it on hand to show you. We'll be graphing it later. So the ball gets hit when it's 1 meter above the ground. Complete the table below to show the height of the ball at various different intervals during the first 4 seconds of flight. So you know what, if you weren't sure about this, you could have gone straight onto the table and then come back to answer this afterwards. We already know that this is going to be 1. And now we're going to fill in our pattern into our calculator, minus bracket x, minus 4 bracket x squared, t squared in this case, plus 16t plus 1. And that gives us 8. Now it's easier to go back and edit these for the other values nice and quickly. So we get 13, 1.5, 1.5 gives us 16. And this is going to be our maximum height, because one of the things that we know about quadratic functions is that they are symmetrical, which means the heights on the way up are the same as the heights on the way down. So it gets up as far as 17 and 16. So you can keep filling into your calculator, but we should know that these, because we're going in the same intervals, and can match this 13, so 17, 16, 16, 13, 13, 8, 8, and 1, like this. Let's just double check the last one to make sure we haven't made a mistake. You know, if they change the intervals, of course, this wouldn't be the case. But yeah, we're back down to 1. So complete the table below. They've given us space to do the calculations, but we just did it straight into our calculator. So there's no need to show any of the calculations there, so long as you're sure that you're correct. Now, on the grid below, draw the graph of the height of the ball while it was in the air. So what we'll do is we'll plot each of these. So this is, remember, with all of these tables, x is always the top row and y is always the bottom row. And then we have our points here straight away. So we've got the point 0, 1, starts here. Then we have 0.58, 113, 1.516, it goes up quite high, 217, and then it's symmetrical, 2.516, 3, 13, 3.58, and 4, 1. And there we go, our very familiar looking quadratic shape there. So we join the points together, not with a ruler, but as smoothly as we can. So we have our quadratic graph like this. Will I get full marks? Probably want to just make it a little bit clearer that that is continuous. No gaps in it. I'll go over my pencil a little bit stronger. There we go. Okay, so there's my graph. Now, use your graph to estimate. So we do want to be as accurate as possible with the graph so that we'll get full marks when we use our graphs to estimate. And we must show the work. If you've used the graph but it's not clear that you've used the graph, you cannot get marks. The length of time the ball was in the air from the time it was hit until it landed on the ground. Now, when's it going to land on the ground? We've got to continue our graph like this, about 4.1 seconds. So we've continued our graph. Let's mark in there. That was 4.1. That's what it looks like to me. So the length of time from 0 to 4.1, 0 to 4.1, and the time was, yeah, we were told that it was in seconds. So that means it was in the air for 4.1 seconds. Now, the length of time the ball was 10 meters or more above the ground. So we have to find 10 meters here. And how long? So there I've used my graph. I've shown it. I'm not quite finished. When was it 10 meters? I should really use my ruler for this. So once I hit my graph here, what was the time when it was 10 meters above the ground? There, that looks like about 0.6. Maybe 0.7 actually, 0.7, and this value here, coming down as well. You can do dotted lines or straight lines. It looks like 3.3. So what's the time? So the length of time from 0.7 seconds to 3.3 seconds. So I'm looking for the difference between those. Use a calculator to do that. 3.3 minus 0.7. And I've got 2.6 seconds. 2.6 seconds. So the important thing there is that I've indicated on my graph all of the work that I did. I can't get marks. You may use the graph, but if the corrector can't tell that you've used the graph, you can't get marks for it. Now, then we're asked to do some calculus because we're always asked to do calculus with functions nearly all the time. They want us to find the derivative. So power by the coefficient minus 8, reduce the power by 1 to t, plus power by the coefficient, and the constant is gone. So there is f dash of t, or if you prefer, you can call that dy dx. Use your answer from D part 1 to find the speed of the ball. So remember, speed is the same as dy dx when it had been in the air for 4 seconds. So we're trying to find the first derivative when t is equal to 4. So we're subbing in 4 into this. F dash of 4 is another way of writing it. Minus 8 by 4 plus 16. And that is a minus number, minus 16 meters per second. So what does that mean? It means it's going down at 16 meters per second. And if we look back at our graph again, that's exactly what it's doing. It's going down. So it's hitting the ground at approximately 16 meters per second. Use your answer from D part 1 to find the value of the time for which the ball was descending or travelling at a speed. So they're telling us that speed, they're giving us the answer and they want to find the time. The speed is equal to 8 meters per second. So we're saying minus 8t plus 16. Now it says it was descending, so it's a minus value. So the speed is equal to minus 8 meters per second. So this is the equation that we're trying to solve, and we're trying to find the value of t. So minus 8t is equal to minus 16 minus 8, which is minus 24. And t is minus 24 over minus 8, which is 3 seconds. And that's the answer. Okay, so it seems like they're asking us something really complicated in both of these, but you just have to remember that speed and dy dx are synonymous. If they give you the value of t, you sub it in. If they give you the speed, you put the whole equation equal to it and solve for t. Okay, so that was everything in that question.